Polygon drawing is better, but it's still wrong, as you can see, so let's go do Newell's algorithm. Wikipedia lists how this works, but there's kind of still a lot to think about in terms of implementation. Up here we have some polygons, but that's the player. This yellow line is the viewpoint, and this line right here is the screen. The first step is the z-test. So let's look at the top-down view, and we've been sorting our polygons by this point in the center, and then drawing them from the farthest to the closest. But now we're going to sort them by finding the closest edge to us. So first, starting with this polygon over here, we check to see if the max val contains any of the other polygon's min val. I don't know which one is which, whatever. And if it does, then we're going to compare these two polygons. If this red polygon was all the way out here, we wouldn't have to even compare it against the blue one because it's so far away, right? And same if it was all the way back behind it. But if this red polygon is somewhere within the min and max values of this other polygon, then we have to continue with our checks. So that's the first step, but then we're going to actually go and look at the screen. So it's very easy to draw a bounding rectangle around each polygon. And if these bounding rectangles don't overlap, then we don't need to compare them at all. But if they do overlap, as in this case, even though these two polygons aren't actually overlapping, their bounds are, so we have to proceed to check them. Because actually checking if the polygons overlap is a bit more involved. Compute planar equation of polygon I. Find line from each vertex of polygon J to player. Find intersection of line and plane and compute z-dist to the point. What the frick am I talking about? Okay, so then at this point, we're going to extend this plane essentially outward, and then we're going to check if all the vertices of this polygon are all on one side of it. So this polygon would essentially get its plane extended, and as long as all the vertices are not are in one direction of it, then we pass our check. And then the fifth check, you do the same thing with the other one, and you check to make sure are all of them behind or in front of the plane. And when I say extend outward, I just mean find the planar equation, which you do by taking the cross product of the vectors. So all this I wrote earlier is not totally useless. But also, it would be a lot more useful if our polygon was an object rather than an array, because we're going to be referring to a lot of different stuff. So we initialize it with a set of vertices. Okay, so here's a pretty basic constructor. We just go through the vertices, we push them to x and y positions. Just say var poly equals new polygon. So let's just have the min distance be infinity and the max distance 0. This dot min dist is math.min of this dot min dist and our new dist to point. We do the same thing for max. Okay, so then that's going to give us our min and max z distances for the polygon. So down here in the render quads function, we no longer have dist to mid, but we do have min dist. So we're going to sort it on min dist now. You have to change these from x to dx because we changed that. If poly.maxDist is greater than minDist, then do more checks essentially. If they're not in the same region, then we just move on to the next polygon, so we don't have to do anything else. For say poly.compute plane equation. Okay, and now what do I have written down for how to do a plane equation? What is this math? I don't know. All right, let me just copy this. We're getting two vectors from the points. We're taking the cross product of those vectors, and that whole thing is giving us this. This is the cross product. And it looks like this. What I should do is I should just make it so that the polygon has an A value, B value, C value, D value. Okay, and there we have A, B, and C written out. It'd be really annoying if my math was not correct. Find line from each vertex of polygon J to player. So we want to do an intersection of line and plane. So we have to get our lines now. If this is our polygon J, then we're finding equations for the lines going to each of the vertices of that polygon. So we go through each of our points, we create a vector that goes from the polygon's point to the player's point, which is just x, y, and z here. And then based on these equations up here, we can calculate the intersection point at x, y, z. I'm going to call them ix, iy, and iz for that they intersect x. And after some more replacing, we have our intersect point. And so we're checking, is the intersection with the plane closer or farther than it is with the player? We're just trying to figure out, like, are all of the points on one side of the plane? If this returns 1, then we draw the polygon of the plane that we're giving it first. The next check is the same thing except with poly j instead of poly I. But swapping shouldn't be too bad, right? We just set one of our values to a temp value, then within the quads to draw array, we set it to the other one, and then we set the other index to the temp value. To prevent it from going into an infinite loop, we only want to swap it once, which means that we need to mark how it's being swapped. So then we just check to see if our map has that value. So it'll return true if it exists and false if it doesn't. Okay, I mean, nothing even looks different right now. So at the current order, it's saying that the dark blue top is closer than the light blue side, which is incorrect. We need to switch these. So at this point, like, we're extending out this plane like all the way out like so, right? And then we're looking at, say, this point. We're checking the intersection. Like, the player's over here, and we're trying to draw a line to this. Like, we would eventually hit the plane if it's like down there over that way, but that's in a different direction than the shape is. But then it would still think like the distance is like over here, and it would still like think about like, oh, this distance to the point over here, and then it would think to draw this one first because it's closer. So I don't think I accounted for that. I guess if t is less than 0, we just continue, maybe. That might work. Okay, that looks correct. And it looks correct from the other side as well. Oh, okay. You know what? I think I figured out what's happening. So let's say this is our sort list, 0, 1, 2, and we want to get in the reverse order. So 2, 1, 0. The way that our swap algorithm is working right now is kind of terrible because it's bubble sort and it's also a non-working bubble sort. So let me just work through it. So we'd start with 0 and we'd look at 1 and we'd say, okay, well, let's swap these around like that. And then we mark that we did that swap. So we'd say 0, 1 over here. And then we'd look at 1 and we'd see 2. And we'd go, okay, well, we have to swap these because they're not in the right order. And then again, we'd mark that. So we'd go 1, 2. Right? And then it would look at 2 and it'd see 2 is fine. And then it would look at 0 and it would say, okay, well, let's swap 0 with 1. Except it then goes and checks the already swapped and it says that that's already been swapped. And so it just won't swap it. And that's basically what's going wrong. All right, so here's my alternate way of sorting that will actually end up with things being sorted. So we do the same thing as before, where we have 0 and 1 and we swap them. And as such, we go and we mark that we swapped them. Now we get to 1, and 1 and 0 are sorted, so that's fine. We get to 1 and 2. So now we're going to pull out 2 and we're going to put it where 1 is. But when 1 goes to try to swap with 2, it's going to go and look up at its sorted, and it's going to say, well, actually, it'll know the position of 0, and it'll know that it can't go any farther than that. So it'll go and put 0 in its spot, and then 1 will go in 0's spot. So now we get to 2, and we want to swap 2 and 3. Okay, and same sort of deal, right? We can move 3 over here, right? But 2 is going to go and it's going to look up and it's going to say, well, actually, I already swapped 1 and 2, right? And so it's going to go and try to put 1 in 3's position. But 1, before doing that, it's going to check and it's go, well, actually, I already swapped with 0. So it's going to go and put 0 in that position, and then 1 will go in 2's position, and then 2 will be able to go in 1's position, and so on like that. And then it ends up being sorted while we still like don't swap anything more than once. Okay, so I feel like I'm so close here, but like, look at this. Look, it almost looks perfect, but then you go real close and it breaks. Imagine this square is our polygon, and this sphere represents the minimum distance of the closest vertex. And you'll notice that if we drag the polygon over to the sphere, all of the 4 corners can be touching, but the center of the polygon is actually closer, right? The center of the polygon is flat, so it's inscribed inside of the sphere. And we can just add it to whatever point, because all the points are equidistant anyway, and that's the bounds for our min distance. And here's what I've come up with. So this is a 2-dimensional model of what's happening. PQ would represent this dark blue that's going closer than it should be, essentially. In this model, we think that it's following this arc line here, because that's what the math is saying, but it's really going straight from P to Q. And so this isn't all of cases, because the polygon can be angled in different ways, but in a worst case scenario where P and Q are both equidistant from each other in opposite directions, then we have to sort of assume a lower bound for how much the polygon is popping out, which would be most at the midpoint here. So first, calculating the angle theta isn't too hard. It's just 180 degrees minus this angle of PCQ right here, divided by 2. And then from there, D is equal to R times 1 minus sine theta. So great, now that we have D, we've got the worst case, the lower bound for how far it could be popping out. And the way that we figure out where P and Q should be is by this. From there, we're just going to subtract off this distance from the min distance of whatever our point is. Work for me, work, come on. No, come on, don't do this to me. Okay. Oh boy, now I hit a big snag. So I've labeled these polygons here because this is what their polygon IDs are, but this is kind of irrelevant. But basically, what's happening is that we have a polygon cycle. We're saying that 2, right, so this is polygon 2 right here. It's saying 2 should be closer than 10, which is correct. Then it's saying that 10 should be closer than 11, which it's kind of ambiguous because 10 is this polygon and 11 is this polygon, so it doesn't really matter. And then it's saying that 11 should be closer than 2, which is kind of right because if you extended this upward, then that would be the case. But then this ends up being like cyclic polygons. So I think I have to go and implement the part of Newell's algorithm that I didn't want to implement, which is rasterization and splitting of polygons. Which means I need to figure out how to tell if 2 polygons are colliding. And to figure that out, you can use something called the separating axis theorem, which states that if 2 polygons are not intersecting, then you can draw a line in between them. And there are many possible lines that you can draw usually, but also at least one of the lines is going to be on at least one of the polygon's edges. And if we go and find that line, and then draw a line that's perpendicular to it, we can look at each of the points of each of the polygons and go and project them downward using dot product onto the perpendicular line, and then we can go and do a simple greater than less than comparison to see if one of our points of one of the polygons lies within the range of one of the others. Okay, and miraculously I think I finally got this working, which is great. And wait a minute. Oh, come on. Are you kidding me? I guess the bounds of this are too large. I'm just gonna say equal to 1. Right, okay, and that's why when you get closer, it was fixing itself because you're closer, so the proportion becomes less. And we're back to normal, and we don't have that issue. So we're drawing them correctly now. Fantastic. Okay, so it's like it miraculously works now. Mostly. I mean, there's going to be some issues. I think if you get like up real close, yeah, see, like it's peeking through there, and like what's the deal with that, right? Next time, I'm gonna break this because there's plenty of stuff that don't work, and oh my god, are you freaking kidding me? I'm pretty sure I could get this to break if I just put a diagonal polygon that went at a diagonal to one of these pillars. Though maybe you could split the polygons to fix that, but even splitting just seems really annoying. I mean, splitting is what's actually part of the algorithm. Oh, but you know what's actually, more fun than this? Like, yeah, like this looks great. This is what I'm talking about. Up? Yeah. Oh, wait, yo. Oh, it's like I'm playing Manifold Garden. Oh, that's sick. Oh, look at that. It's like I'm in the land of infinite pillars. Wait, hold on. I bet I could get...